Okay, I've got another pair of equations here. Can you please have a go at solving these simultaneous equations, and I'll come back in a few seconds. Okay, hopefully you've had a go at trying to solve these. Now, for this particular question, we have different coefficients out the front of our y's, and if we were to do a elimination method straight away to say get rid of these x's, that wouldn't help us because we would still be left with x and y's in our combined equation. And the purpose of combining these equations initially is to eliminate one variable, to bring it down to one equation with one variable. So we still got to try and get rid of these y's. Now, if I label this as equation one, to make these have the same coefficient out the front, so we can use either the substitution or elimination method, I need to scale equation one by a factor of two. So 2 times equation one gives me 2y minus, 2y is equal to negative 2x plus 4. So I'm scaling both or every term in that equation by a factor of 2. Let's just call this one's equation 2. Let's call this equation 3. And so I'll be using equations 3 and equations 2 to solve this simultaneous equation. So I could use the substitution method, for instance, and have, say, negative 2x plus 4 is equal to 3 on 4 x squared minus x plus 4. And now I want to bring all of these together onto the one side of the equation. So 0 is equal to 3 on 4x squared minus x plus 2x, so positive x, and then plus 4. Well, that's a plus 4 on either side, so they can just cancel each other out there. Now, my c value is going to be 0 in this case. So I could plug this into the quadratic equation, or seeing as there's an x in both terms, I could factorize x out of this. And I could say 0 is equal to x 3 on 4x plus 1. Now, if I was to divide both sides by x, they'd be leaving just this bracket behind because that once you divide x, that goes to 0. But that'll just give you one solution. It's easier to see that we have two solutions if we note that we get a solution when this is equal to 0, and we get a solution when this is equal to 0. So we're applying the null factor law to this. Now, so x can equal 0, and and 0 can equal 3 on 4x plus 1. And so we will have a negative 1 times by 4 on 3 is equal to our x value. So negative 4 on 3. Now we can plug these values back into one of the starting equations. So let me just rewrite this on a fresh page. Okay, so I've written this out on a new page. I've got the important bits of information here. So I've picked just the simplest equation, and I've got my two valid sets of coordinates for my x positions. Now let's find the y positions. So we plug x equal to 0 into the equation. So y of 0 is equal to negative 0 plus 2. That gives us a positive 2 value. So when x is equal to 0, y is equal to 2. And the other equation, we're plugging in negative 4 on 3. So negative 4 on 3 plus 2. We get negative negative, so we get a positive 4 on 3 plus 2. And 2, we want to scale to have that same common denominator. So let's just multiply it by 3 on 3. So we have plus 6 on 3 there. So when y for x of negative 4 on 3, our y value is positive 10 on 3. This would be 10 on 3. Now, these are our exact values. We could also represent this as a mixed number, or we could represent these as decimals if we aren't after exact values, but instead approximations. Okay, I've got another pair of equations here. Can you please solve these simultaneous equations using the simplest method? And I'll come back in a few seconds. Okay, hopefully you're able to solve these. Let's go over it. Now the y values have the exact same coefficient, so we can just say x plus 3 is equal to x squared plus 6x plus 9. Now it looks like this could actually decompose into two factors, but let's just go with this technique for the time being. Now we're moving all of this over to the other side, so we got 0 is equal to x squared uh, plus 5x plus 6. Now I know that this could decompose as well. So this can just decompose into, using the Australian method, this would be, so 1 and 6, what are the factors of 6 that add to 5? Well, 2 and 3. So x plus 2, x plus 3. Now, applying the null factor law, um, this is true when this equals 0 or when this equals 0. And so our x solutions are x is equal to -2 and x is equal to -3. We can then plug this into the simplest of the equations, which is the x plus 3 equation. So y of -2 is equal to -2 plus 3, which is equal to 1. And y of -3 is equal to -3 plus 3, which is 0. And so our two sets of coordinates that are valid for the original simultaneous equations, -2, 1, and -3, 0. And that's the solution for that question. Now, an alternative approach could have been, you might have noticed that this could have actually decomposed into y is equal to x plus 3, x plus 3, because you have your a and c values multiplying together to give you 9, factors of 9, 3 times 3 gives you 6. And then you could have used the substitution method on these two equations. So you would have had x plus 3 is equal to x plus 3, x plus 3. Dividing both of these by x plus 3, you have 1 is equal to x plus 3 times by x plus 3 all over x plus 3. Or you could have subtracted this from both sides. So if you divide, you're left with a 1 there, not a 0. And then you've got to subtract 1 afterwards. Or alternatively, you just do that subtraction at the start so that you don't have a fraction that you're dealing with. And so you could have had 0 is equal to x plus 3, x plus 3 minus x plus 3. Now, with this approach, you can factorize out x plus 3. So 0 is equal to x plus 3, leaving behind x plus 3 minus 1. So you've got 0 is equal to x plus 3, x plus 2, and then again using your null factor laws, you would have x is equal to -3 and x is equal to -2. And so that's just an alternative method to being able to find your x values, and then you would plug that back into the equation like we did before to find out what those y values would have been. And I think we'll leave it there for this video.